So how to take an element? So for this chapter, electric charges and field, and also for whole electrostatics. This method, taking an element, is very useful. Okay, it's pretty useful. There are a lot of questions that can be solved by taking an element. Once you get hold of this method, then there is no problem regarding solving any problem from electrostatics or even magnetostatics. Okay, this method is also applicable for gravitation. Okay, so basically we are covering three chapters: gravitation, electrostatics, and magnetism. Okay, so first of all, let's say there is this rod is given and it is having some lambda charge density. First of all, remember this: almost always, if they ask you, I mean, if they give you a rod, that means it is having a lambda linear charge density, because it's a basically a one dimensional object. Okay, you can take it as a line. Okay, just a minute. Okay, so almost always they will give you a lambda charge density. Okay, and they ask you to find electric field at this point or whatever. Okay, so first, if you encounter any rod with a lambda charge density, just take an element anyway. Okay, let's say you are measuring something from this side. This is origin. First, start with the origin. Okay, so then we are going to take an element whose length is dx. Okay, since this is a charge density, then we are going to assume that it is having a charge dq. Now use this analogy, or we can say direct method, that for let's say it is having total charge q. Okay, or in another word, we know that lambda linear charge density is given by total charge upon length, right? So for this element, what is total charge? It is dq. And what is length of it? It is dx. So dq will be lambda dx. Once you get the charge, then things will get over, because we know that electric field is given by kq upon r square. Almost lot of thing depends on the charge directly, right? So I'm not discussing the whole problems. I'm just giving you an idea how to take an element and how to proceed. Okay. For example, there is this question of gravitation, let's say. Okay, so in gravitation, they will give you a mass density. Okay, mass density is given by mu. Mu is basically mass upon length. Charge density is charge upon length. So you are going to take an element of mass dm and length dx. This is origin. Origin is important. Okay, whether you are taking it. So the next step would be that this distance is there. This distance is x. And then you are going to integrate some things. Okay, whether you are finding electric field or potential or etc, etc. So let's say at x distance you are taking an element of length dx. So here the dm mass would be what? Dm upon dx. So dm will be mu dx. Understood? Okay, one important thing, it is also important from where you are taking an element. Okay, basically we are talking about origin. So let's say there is this rod is given whose charge density is lambda, let's say, and it is having a length l. But if you take origin from its center, this is l by 2, this is l by 2. Okay, and you are taking this line as an origin. Okay, so what we are going to do, we are going to take an element of, let's say, charge dq and length dx. So we know that uh, this is l by 2. Okay, not mu, l by 2. Okay, so Here the charge will be dq by dx, right? Dq is basically lambda dx. Okay. But when you are going to apply integration for anything, like you are, finding an electric field, it is given by k dq upon, let's say it is x distance away. Okay, so it will be x square. So here limit will be from 0 to, in this case, if you are finding the electric field where we are taking its origin from one of its end, then the limits will be 0 to L, okay, 0 to total length. But in this case, the limit will be, this is minus L by 2, right? And this is plus L by 2. The limit will be minus L by 2 to plus L. This is the difference, okay? Nothing else. Are you getting my point?
Yes, sir.
So this is the rod, okay? How to take an element in rod. Let's say a cylinder is given. As we have discussed earlier, let's say there is this charge Q. The question is to find out the electric flux from this surface, okay? Or electric field.
Okay.
So as you can see, we have taken here the linear element, right? Which is of length dx. We have not taken any surface element or volume element, right?
Yeah.
But here, this cylinder is a three-dimensional thing, okay? Basically two-dimensional,
So we need to
three-dimensional.
take volume.
No. So here we are not taking volume. It depends, okay?
Okay.
If the charge density is surface charge density, whether it is volume charge density, okay? So this is a basically disk, okay? Because it's a solid cylinder. In this solid cylinder case, we are going to consider a ring of radius x and thickness dx. You can call it a ring or disk also, because the ring does not have any thickness, right? But this one is having dx thickness, so it is basically a disk, but it is basically a ring, okay, having thickness dx and radius x. So when it comes to its area, always write area of this ring. Let me enlarge it here, that this is the ring we have taken. Just a minute. Sorry, Jivika.
It's okay, sir.
So it is having a thickness dx, okay?
Okay.
So whenever you try to write down its area, don't write it this way, okay? Pi x square. Because then you will not be able to write dx, because then here it is having a power 1, so it will become x cube, right? So that's not the right way.
Right.
Okay, almost always student do this mistake, to write down its area as pi x square, which is wrong. Write it down this way, that its perimeter multiplied by its radius, okay, 2 pi x dx. So dimensionally, if you see, it is having power 1, this is having power 1, so it will become x square, basically meter square, right? So this is an area.
Yeah.
And then if you are finding the electric flux, then you are going to require an area, right? Because it depends on area. So instead of ds, you can write this area, okay, and integrate it.
Okay.
Because there is this charge, this is, let's say, r distance, okay, it is making an angle theta. So eventually you are going to write this cos theta in this r and x form, right? So if you want to write cos theta in this triangle, so cos theta will be r upon under root r square plus x square. So that's how you can transform this mathematical equation which was given in terms of theta. So you can transform it into the distance. Also you can write this area in terms of this x, so that you can integrate it. Are you getting my point?
Yes, sir.
Okay. Now the last one, let's say a sphere is given. So almost always they will give you volume charge density in terms of, I mean, in the case of sphere. Okay.
Okay.
As I've told you, this method is also useful in gravitation. Okay.
Okay. Okay.
So what we are going to do here is to consider a small sphere of radius x. This is, let's say, having a radius r. So almost in everywhere, I mean, in each case, this was rod having length, right? So we considered a length element.
Yeah.
Here it was having a regular, I mean, circular shaped area, right? So we considered a circular shaped element, right? And here it is having a symmetry of
Yeah.
sphere. So we are considering a spherical element. So it is that simple, okay? If you are having spherical symmetry,
Okay.
then spherical element, okay? If you are having circular
Yeah.
symmetry, then you are going to consider a ring element or disk element, okay? And you are having a length of something, let's say rod, you are going to assume a length element, okay? Or linear element. Yes, linear element is a better word. So it's that simple, okay? It's not a big thing. So in volume charge density, you know that it is Q by V, right? So let's say this
Yeah.
innermost sphere is having charge Q1. We are considering it, okay? So this will be
Okay.
Q1 by, what is the volume of this smaller one sphere? It will be 4 by 3 pi x cube. So that's how you can write this charge, and then you can proceed to find electric field, electric potential, blah blah blah. Understood? Okay. There is
Yeah.
also one method using angle. You can find some things. Okay. For example, you are having an arc. It's
Okay.
having a lambda charge density. Okay. It's a spherical arc, basically 1/4 of a sphere. Okay. Sorry. It's a circular arc, and it's a 1/4 of a circle. Okay. And you are interested to find electric field or a magnetic field at this point P. So how you are going to find it? So first, origin is necessary. Okay. In linear elements, origin is necessary. It depends from where you are taking an origin. So here what we are going to do, since it is an arc, okay, so instead of taking a length element, we can take an angle element, right? I made up this word, okay? There is no word, proper word like angle element.
Okay.
I made up this word, okay? Angle element means we are going to consider an element of length, let's say ds, and its substance and angle, let's say d theta, okay? How much it is? D theta. And
Okay.
with the origin, it is making an angle theta, okay?
Okay.
So we know that arc is given by L is equal to r theta, right? Radius
Yeah.
multiplied by angle. For this ds can be written as, this is, let's say, r distance, okay, radius. So r into d theta. So you can actually write ds in terms of theta angle, right? So now
Yeah.
let's say this is having a lambda charge density, right? linear charge
Yeah.
density, and it is given by total charge upon length, right? So let's say its original length was L, okay, total length.
Okay.
Okay, so here in this case, for our element ds is the length, okay, or let me call it dl, okay, it will be easy for us.
Okay.
So the charge on this smaller one element will be q1 by dl. It is very simple. Q1 is lambda dl. And what is q1? What is dl? It is rd theta. Now you can find electric field. For example, here the electric field will be in this direction since it's a positive charge, right?
Yeah.
So if this is an angle theta, then this will be an angle theta, right?
Yeah.
So in this direction it will be e sine theta. In this direction it will be e cos theta. Yes or no?
Yes.
No, no,
Yes.
no. With the origin, right? So it is e sine theta here and it is e
Sine
cos
e cos
theta here. Okay. So same way,
Yeah.
if you take an element here, okay, it will give us in this direction, I mean opposite to this e cos theta, there will be e cos theta, so that e cos theta will get cancelled out and you will get here 2 e sine theta, okay,
Okay.
and then you can integrate it, okay. Now it's upon
Yes,
you,
sir.
but the method is this. What's the method? That since this is an arc, the angular element can be very useful. So just convert this length into angle, then the things will get easy.
Okay.
Okay, so right now that's it for it. But in future, I will give you more examples on how to take an element. Okay, there are two or three methods also, but it is too advanced. Okay, too advanced for
Okay.
JE also.
Okay. Okay.